Hey everyone, welcome to today's Explainer. We're jumping straight into the absolute beating heart of machine learning today to demystify a dense academic buzzword. And honestly, it holds the actual key to how artificial intelligence works. The term inductive bias. I know, it sounds super technical, but stick with me, because by the end of this explainer, you are going to see exactly why this concept is literally the unsung hero of machine learning. So, I want you to really think about the word bias for a second. In our everyday lives, and especially when we're talking about tech and society, bias gets a totally bad rap, right? We're constantly worrying about societal biases sneaking into algorithms and messing up results. But what if I told you that in the realm of machine learning, algorithmic bias isn't just a flaw, it's actually a massive feature? Seriously, it's the fundamental engine of intelligence. Without it, learning isn't just hard, it's mathematically impossible. Okay, let's dive into this. Here is our roadmap for today. First up, the good kind of bias. Then we'll look at the infinite search space. After that, the incredibly named no free lunch theorem, followed by engineering the right features, and we'll wrap the whole shebang up with the human element. All right, section 1. The good kind of bias, a necessary anchor. You know, when most people think of machine learning, they immediately picture hard maths, incredibly rigid rules, just perfect calculations. But the reality? The model development process actually requires a shockingly heavy dose of guesswork and intuition. There are no hard and fast rules for predicting the future. And that brings us right to our core definition. Inductive bias is the tendency for a system to prefer a certain set of generalizations over others that are equally consistent with observed data. Think of it like a giant anchor. It's the core assumption a model makes to connect the dots. Without this crucial anchor, an algorithm simply cannot generalize from past examples to make predictions about brand new, totally unseen data. Moving right along to section 2, the infinite search space, and why we fundamentally need this bias. Let's actually prove mathematically why a completely unbiased system is completely useless. We'll look at a classic thought experiment from the source material. Imagine we want an algorithm to learn a mapping for numbers from 1 to 100. They can either be labeled true or false. The algorithm observes that 2, 4, and 6 are labeled true. It also observes that 1, 3, and 5 are labeled false. Now here's the test. What is the label for the number 7? To a human, this is a total no-brainer. We instantly spot the pattern. Evens are true, odds are false. So 7 must be false. Now, what's really interesting about this slide is how an unbiased machine looks at that exact same problem. It doesn't inherently prefer simple patterns over complex ones. It just looks at the remaining numbers from 7 all the way up to 100 and realizes there are 2 to the 94th power possible labelings. That is a massively huge number. In half of those billions and billions of universes, the number 7 is labeled true. In the other half, it's labeled false. Because the machine has absolutely no bias to prefer the evens are true rule, it's paralyzed. It is quite literally reduced to random guessing. And that leads us to this incredibly powerful quote from the material. Without inductive bias, a learner can't generalize from observed examples to new examples better than random guessing. That belief, the foundational assumption that a simple pattern like evens are true is just way more likely than a totally random, chaotic labeling, is the only thing that makes both human learning and machine learning even possible. So, if we need bias, which bias is the best? That brings us to section 3, the no free lunch theorem, and why there's no master algorithm. The no free lunch theorem mathematically proves that there is no single master algorithm out there. There's simply no universally best bias. If algorithm A beats algorithm B on one specific set of problems, algorithm B will actually beat algorithm A on an equally large set of problems. And get this, that's true even if algorithm B is just randomly guessing. So finding the best model isn't about hunting down some perfect master algorithm. It's about finding the algorithm whose inherent biases perfectly match the very specific problem you're trying to solve. Let's actually compare two entirely different biases to see how this plays out in action. On the left, we've got logistic regression. Now, this guy is biased toward linear boundaries and independent terms. It's absolutely fantastic for identifying if a patient has metastatic cancer just by spotting independent buzzwords in clinical notes, words like METs or chemo. But on the right, we have deep learning models called LSTMs. They have a totally different bias. They preserve long-range contextual information. If you're trying to extract complex genetic test results from a massive multi-page PDF where the context around the words matters just as much as the words themselves, logistic regression totally fails. But the LSTM, it shines. Moving on to section 4, engineering the right features.
This is all about aligning your data and your bias.
Okay, so once you pick the algorithm with the right bias, you can't just toss raw data at it and hope for the best. And honestly, there is a super common trap here. It can be incredibly tempting to just dump as much information as possible into your model, assuming, hey, it'll figure out the patterns. But listen, more data isn't always better. Sometimes less is genuinely more. Dumping too many features into a model can cause a major headache called overfitting, where the model just memorizes noise instead of learning the actual underlying pattern. And this is especially dangerous in non-consumer tech applications where carefully labeled training data is really scarce.
Let's look at how this works in practice with clinical health notes. If you just feed the model a raw word count, basically assuming that the more a doctor typed a word, the more important it is, your model is probably going to fail. Why? Well, because it turns out doctors are human just like us. They constantly copy and paste older notes into new ones. The word count is essentially lying to the model. But if you strip away all that extra data and just use a binary representation, simply asking, did this word occur, yes or no, it suddenly becomes highly effective. You've aligned the data with reality.
And this brilliantly illustrates another great example from the source material regarding genetic test results. In the raw data, you might have hundreds of different percentage scores, ranging from 1% all the way to 100%. But your model only really needs to know if the expression level is broadly high or low. By converting all those specific, noisy numbers into just two simple engineered tokens, like less than 50% and greater than 50%, you haven't added any new information, but you have drastically reduced the noise. Instead of trying to learn 100 separate coefficients, the model only has to learn 2. And this perfectly aligns with the linear model's inductive bias because it prefers to learn fewer coefficients with higher magnitude values. Finally, Section 5, the human element and how we guide the machine. We've talked a lot about math and data structure so far, but to summarize exactly why we as human beings absolutely must inject inductive bias into our models, just take a look at these core reasons. First, feasibility of learning. Without it, models just wildly overfit to noise. Second, beating the curse of dimensionality. It shrinks that massive infinite search space we talked about down to something a computer can actually handle. And that leads right into the third point, computational efficiency. And finally, incorporating domain knowledge, which literally allows us to inject human expertise directly into the machine's architecture.
So the crucial point here is that there's no magic formula you can just download off the internet to solve your specific problem. Finding the right bias is a profoundly human endeavor. You really have to start by sitting down with subject matter experts to understand how they naturally approach the problem. Then you perform exploratory data analysis. And finally, you conduct error analysis on documents the model misclassifies to see exactly what linguistic patterns are confusing it. It is all about engineers partnering with domain experts to perfectly encode human perceivable patterns right into the mathematical model.
Machine learning might seem like this magical way to completely bypass human intuition when you're trying to crack a tough problem. But the exact opposite is true. Successful AI is ultimately driven by deep human expertise and really well-chosen intentional biases. So I want to leave you with this thought-provoking question as we wrap up today's explainer. As we move further into the age of AI, will you rely entirely on cold algorithms to solve your problems, or will you step up and use your unique human intuition to guide their learning? Think about that the next time you hear the word bias. Thanks so much for joining me on this deep dive.